Okay, so in today's quick workshop, we will cover how to install Anemone in Grasshopper and quickly go through how to run the loops in case people want to try these modules assignment in Grasshopper. And then we will go through how to install Ladybug and a quick example on the solar radiation in Grasshopper as well. So the first step is to go to Food for Rhino, which is the website where you will find all the packages for Rhino and Grasshopper, and type Anemone. This is the most used package for looping in Grasshopper. So then you want to go and get the latest version, which in this case is Anemone 0.4. So you click download and just save it somewhere you know it. Let's say, well, I won't download it because I already have it. But once you download it, you would have to go to Grasshopper, then click File, then go down here to Special Folders, and then click on Components folder. And that will take you to the path where all your packages are stored. So when you do that, you'll probably see this empty. Maybe you'll only see Lunchbox. So the goal here is to copy and paste the Anemone file that we just downloaded here. So in this case, it's just a Grasshopper file. And you just copy and paste it here, and that's pretty much it. Then you close here. You have to close Grasshopper and Rhino, and then open it again just to make sure that it gets installed. And then you'll see it up here anyway. So once you do that, I'll just show you how the looping thing works. So looping in Grasshopper works a little bit different than in Dynamo. Instead of using a list map to loop our node, like our function node, here it's more like a physical loop. So it basically starts with a start loop node, which is this one. And then you close it with a loop end. So in this script that I have here, I'm reading Excel values in which each row represents a generation of a simple building. And then these groups right here, what are doing is actually creating that building. So let's start here. I'm just creating a couple of profiles here, and I'm extruding them to create a building, a loft. And at the very end here, I'm just getting the volume, surface, and floor area, like in the assignment of module 5. So this would be like my function in which I will just give some inputs, such as the scaling factor and the total height of my building. And those values would be pulled from from an Excel sheet that I have stored here. So you can see I'm using a path node in which I saved the Excel file. And then I'm just making sure I'm calling the right sheet. And then this will give me all my values. So for example, here I have 9 values for my total height. And here I have 9 values for my scaling factor. Now, over here, what I'm doing is doing some transpose of matrices, and I'm getting the 2 variables. So I just want to get the list of values for heights and the list of values for scaling factors. And then I'm going to start looping into one by one individually. So that's where the index comes from the loop after I start advancing from index 0 to 1 and all the way up to 8, which would give me 9 generations. So far, this is just Grasshopper nodes, regular nodes, but these 2 here in the green group are the ones that are going to be looping around. So I'm just going to pull this one close to show you how it works. So essentially, the loop start and loop end connects the inputs and the outputs, and then it allows you to kind of move through indices inside. So the main input here is the number of generations. So this is n, the number of repeats that you're going to loop through. Then you have a trigger, which is very important because if you don't have a trigger, your loop will start running automatically. So you want to control that. And then you have your variables, which are labeled as D0, D1, D3, etc. And you can change the name of each variable by right-clicking and then just changing the name here. So in essence, the loop pretty much expects a number of variables in the left side and will give you variables in the right side. So make sure you have the same number of variables going in and the same number of variables going out. You can use different variables than the index, but in this case, the index is my only value that I will be moving from cell to cell in the Excel. So I'm just starting my index in -1 because I want to call in the first iteration. When I add 1 to that index, I will be in index 0, and that will give me the first value of the height and the first value of the scaling factor in this case. So that is a nice approach if you want to make sure you start with your first value in your Excel. And then I'm just putting here placeholders for my report values, which are volume, surface, and floor area, that are going to be coming here, flattened, of course, because I'm going to store them in panels, and that later we can export those to Excel. So there's another important thing to make sure you do, and it's if you want to see the whole process of the looping, you would need to record your data. So make sure you right-click your loop end node and make sure you have this selected so you can see the data for each iteration. If this is not selected, you will only see the last result, which would be in this case a height of 110 units and a scaling factor of 0.2. But we want to see the results of all those three variables, volume, surface, and floor area, for all 9 different combinations. So that's pretty important as well. So that being said, I'm going to show you this little iteration script in action. So this. So here I have my shape. So the current iteration, as you can see, is a top scaling factor of 0.2, which you can pretty much see here. It's taking the initial profile and then it's rotating it by a certain degrees and scaling it. So 0.2 is pretty small, and then a height of 150 is the total height between my 2 profiles. So once I hit true here, once I change the trigger to true, what's going to happen is that what's coming out of here would be a -1, and it will be adding 1 to that -1, which would be 0. And then this would be the index from which I will start extracting data here. So let's say when I run the first iteration, I will get 110 units of height and 0.8, and that will be my first iteration. Once that's done, we'll be here. We would have a new shape, and then we would get all these metrics that we're interested in. For this assignment, here's where you'll put energy analysis if you want to, or directness of a view, or how unblocked your view is with respect to a context of other buildings. Here's where you can get creative. Just make sure to connect the beginning with an index or with a variable. It doesn't have to be an index. And then the output would be your metrics. They could be adjusted, you could add formulas or whatever, but just make sure you're always pulling them out in the end. So here is where we will see the actual generations. At this moment, the trigger is set to false. So I'm just looking at the volume, surface area, and floor area for the first, for these values, 0.2 and 150. So I'm gonna hit true here and we'll see, hopefully, this thing running. So that's the first one, second, third, fourth is pretty tall, fifth, and so on. So let me just wait until this is done. Looks like it's done. So here we have like the record of each one of those generations. And then here we can use the Excel export node, which works exactly as in Dynamo. You just need a file path, a row to start writing your data and your data. So that's pretty much the big concept of anemone. It's quite simple. And again, just think about it as a function of X. And X would be your parameters. One thing that goes in this case, my function would be all this. And the goal of my function is to create the shape. And the inputs could be heights, angles, scaling factors, or whatever that creates geometry. And then just think of a loop that will go over a number of iterations. So that's the basics of looping. Now I'm going to show you how to download Ladybug and how to install it. It is a bit tricky. So let's jump right in. So again, back to Food for Rhino. At the end, you're going to look for Ladybug. So Ladybug includes many other tools. So it's not just one package. It also includes Honeybee. I think, okay, so here's here's like how they all connect with each other. There's Butterfly for CFD. There's many options here to play with. I think there's another one that's missing here, but yeah. Essentially, we're going to use Honeybee and Ladybug for radiation analysis. You can explore others if you're interested and if you have time. And here we're going to download this one, which is pretty recent. It's on the top. It's Ladybug Tools 1.2.0. And then you're going to hit download. And that download would be a zip folder. So you want to first save it somewhere safe, for example, here. And then you have to unzip it and then copy the folder in the same way as we did here. So I'm going to open Grasshopper again. And then you want to go to special folders, components folder, and then you have to paste the unzipped folder. You won't see this one because this is the result of the installation. So that's what we're going to do right now. I'm going to show you how to install it because you need to do an extra step. So you have to double click here in the installer. So this would actually, I'll just open a new instance of Grasshopper because I don't want to crash my computer. So I'm just going to directly open that file. So that's model 6. Okay, so I have to unzip it first. So this is the one I want to open. So it takes a little while, so be patient because it's quite heavy what's going on in the background. So this is the instructions for the installation. So it's as simple as double clicking the first toggle. And once you double click it, you'll install Ladybug. And then you just double click the second toggle here. It takes a while, so just be patient. In my computer, it took like a minute or two. So just make sure you click this one first, and it will tell you if there's any error here. I won't do it because I already have installed, and that might give me an error. But just remember, double click the number 1 first, and then the 2. It's pretty straightforward. And then the same process, you have to close Rhino, close Grasshopper, and then open it again. And then you'll see all of them here. HP Energy, you'll see Dragonfly, Honeybee, and HP Radiance. So that is the basic workflow for that, for installing it. And now I'm going to show you a basic workflow for doing a radiation analysis in Grasshopper. So this is actually an example that I took from the website. I modified it a little bit to explain you guys the steps, but it's pretty straightforward as well. So let me just open this one. So we have two pieces of geometry here. We have first, we have in white, we have our test surface. So our test surface in this case would be like the ground. So in this case, what Ladybug developers are trying to teach us here is how we would study radiance on the floor based on shadow casted by other buildings. And that's our other piece of geometry, the buildings. So in this case, it's just a rep or a collection of surfaces that are grouped together, pretty similar to the example of the views in the city that Glenn showed in the kickoff session. This is just a collection of surrounding buildings. So this is where it starts. Then the step 1 would be to obtain the Energy Plus weather file. So that could be either EPW file or a stat file. In this case, we're using Energy Plus, so the actual example provided us with this link. And what this link is gathering is just the data for a particular point in the US. In this case, it's somewhere in Philadelphia. And I think it's because Ladybug developed, like their headquarters is actually in Philadelphia. So yeah, what this is doing is just getting the weather file. I added here a panel to see that it just saves this weather file in your computer in the Ladybug folder. So that's step 1. Step 2 is to generate the sky matrix. So the sky matrix pretty much needs only one input, which is your EPW file. You could also get more complex, and this is one thing that I would recommend if you want to explore like very particular values, and it's the sky density. So in the sky density, it's just a parameter of 0 or 1. By default is 0. And what the difference between those two is the way the sky matrix is assembled. So there's 2 ways of creating a sky matrix or panelizing the sky dome. The Treganza way, which uses a few number of panels, and the Reinhardt way, which is a little bit more granular. So if you want to get like more detail, add more detailed simulation, you would just add a number here, a slider with 1, and this would make your analysis way more complex, and it will take longer. So you might not want to do that. And then this one has a toggle as well, a trigger, which is set to false initially while I explain the steps. Then after creating the sky matrix, this essentially would just be a file as well, which would be read by the sky generator, which is this node right here. Select sky matrix. It takes your sky matrix and it gives you other options as well. You can select the hour of the year to make the analysis. So this could be a particular hour in the year. So it's a value from 1 to 8,760, which is 24 hours per all days of year, 365. So you could choose just one point in the year or a range as well. You can select an analysis period. In this case, it's left empty because we want to check all of the hours of the year because we're doing a cumulative analysis. So we're just adding up everything at the end. And this is the main input, the sky. Here's where you create the sky, in fact. And this is what serves as the main input to run the analysis. So this node right here is where you pretty much run your study. The main input is the geometry. So let me pull this here closer. So here we have our piece of geometry that we're going to analyze. That's geometry. Our context, which in this case is our city buildings. And then a grid size. So the grid size in this case is linked to the actual dimensions of my geometry. So for example, my Rhino is in millimeters, I believe, or centimeters. So if I have a grid size of 4, it will create 4x4 tiles and it will analyze the radiation on each one of those tiles. So the smaller the grid size, the longer it will take to run your simulation. So you might want to start with a large grid size and test it first. There's another input here that is the distance from the base. So this input here, it's just a way of making sure you're hitting the right surface. So what this is doing is, so we're taking our base surface, which is this one, the one we want to analyze. And what this is doing, it's just giving a little offset of 0.01 units upwards, just to make sure that we are studying our surface, but a little bit above to get the sun radiation. If you run the analysis and you see that there's nothing coming out of here in the results, it might be that your surface normal is pointing down, and that's why it's not getting any sun when you run the analysis. So that's why you use the distance from base. If that's the case, you might want to use a flip to change the orientation of your surface. So a way of getting to know that is using a node like to get the normal, plane normal or surface normal. So there's many ways of doing it. Then here, the next input is the orientation study. So this one is optional. We are not going to, we don't need it for this purpose. And the most important one is the sky, which is the one that's going to give us the values for the radiance in our study. Let me set the parallel input should always be set to true, and then the run it. That's pretty much it. And then the results would be basically the radiation result, which would be in kilowatts per square meter. So you might, I mean, if you're giving some sort of weighted average to your metrics, here's where you want to be careful of your units. Maybe you want to do some conversions to feet if you work in imperial systems, or if you have other ways of measuring your energy or the cost of that energy, then be consistent with the units. And finally, there's some optional step here in which we'll visualize the radiance. So this is like the most exciting step, because here's where we actually can put like a name to our graph. We're going to do a mesh and kind of give it a small offset and color based on the radiance values. So I'm going to start running this. And the first step, well, it's automatic. It just gets the file from the website. Second step is to generate our sky. So I'm going to double click the toggle, which would make it true. And then it's running. I can see that it's taking a bit to process. So at the end here, we should get our sky matrix, and we should have created our sky in Grasshopper, sorry. So exactly that's what happened. Here we got that it extracted the data from Philadelphia in a particular location. I'm not sure what's the nomenclature here. And then here we have our sky matrix. So this is just a huge list of values. It's like a time series of weather values, which I'm not entirely sure how to interpret this, but that's why we have this node here. So far we have our sky, we have our analysis geometry and our context. And we also define the grid size to do the radiation analysis. So what I'm going to do next is I'm going to hit run, and this would take like a minute or two, because we'll be working with a lot of small tiles in our surface. Yeah, so I can tell it's running because I'm panning through the script and it's not moving. So it's generating all those results. Okay, so here we can see that it gave us all the values for radians. So remember, these are all kilowatts per square meter. Yeah, kilowatts per square meter. And these are the values for each one of our points. So for example, you can see that there's some that are 0. These values here correspond to points that are covered by buildings because they don't get any radiance. And then there's some max values around the edges because probably these points are points that get no shade at all in the whole analysis. So that's why they are so big. And then finally, we can visualize this in a mesh. So I'm going to turn this on. So this is what it looks like. A little bit. So this is just the tile that you can customize here, your units, and that's it. So another way of visualizing this would be like giving a volume to your little tiles, like an offset, and that's what I'm doing here with this domain. It was originally higher, like this was I think 10 or something, but this is what would give you like some sort of like bumps here in your surface. So this could be interesting when you are testing your building shape, kind of to give some visual feedback of what areas of your building are getting more radiation, probably what areas need more insulation, and so on. So yeah, I hope this kind of gives you the big picture of how to run studies. Again, I'm still trying to figure out how to transfer this whole workflow into, instead of a flat surface. I would be more interested to see how this affects a complex shape or a set of tiles or panels. So yeah, that would be the next step. But I think so far this would be a great starting point for you guys to start cranking on it and figuring out how it works as well. So yeah, that's pretty much everything for today's workshop. So I'll be taking questions if there's any. If not, let's go to office hours and yeah, just. Yeah.
I have a question, but not really like about what you just talked about.
Okay, let me stop the recording.
So whenever I